Dear students, Assalamu alaikum. Welcome to week 6 of online machine learning sessions. In this session, we will try to finish our support vector machine algorithm which we started in our last lecture. So we already completed most of the stuff related to support vector machine in our last lecture, and there were some bits remaining which we will be covering in this session. So the earlier part of this session will be covering support vector machine. After finishing support vector machine, we will move on to our next domain, which is unsupervised learning domain, and we will be studying clustering there. So as you know, the algorithms which we have covered so far, including support vector machines, neural networks, and other naive Bayes decision trees, all these algorithms, we studied these algorithms under supervised learning domain, in which we had a target class, or we had the output values, and we trained our algorithm based on that target class, and then we performed classification on the testing data set. After finishing this supervised learning domain, we will be moving on to unsupervised classification or clustering algorithms, you can say, in which we don't have a desired output or the target class, and we try to make different groups of the data set based on different patterns. So we will be moving on to this new domain in the later part of this section, but initially in the earlier part of this session we will be discussing the support vector machines. After covering clustering algorithms, we will have some final thoughts on the semi-supervised or reinforcement learning algorithms, and then we will be discussing how can we measure the performance accuracy of these different algorithms belonging to semi-supervised, supervised, or unsupervised learning domains, and then we will be concluding our lectures. So moving on to support vector machines, let me give you a quick recap of whatever we had discussed in the last lecture, and then I will explain in depth from the point where we left off. So as you know, that support vector machine is basically a classification algorithm. It is also used for regression problems, but most of its usage is for classification, and that too in under the supervised learning domain. So in the starting slides, I give a little bit of definition and a bit history of support vector machines, and then I basically related support vector machine with the logistic regression, which we covered in detail. So the problem which we basically had in a logistic regression is that we could have multiple decision boundaries, right? So a decision boundary is a line which can classify two different classes or which can separate two different classes. So when we have multiple decision boundaries, like in logistic regression, which could successfully classify two different sets of data into classes, then it becomes difficult for us to select the most optimal line, because what happens is when we add new data points or new samples into our algorithm, then it can happen that the decision boundary which we have selected previously may not work for the new data points, and in that case the accuracy of the system can drop down. So we can summarize that in logistic regression we don't have a thought through process, or we don't have a logical decision on the basis of which we could select the most optimal decision boundary. But in logistic regression, in support vector machines, we have the concept of margins, and we try to have the maximum margin. So we described all these terms were about a decision boundary, a hyperplane, and what is a margin is, and what a maximum margin and what a minimum margin is. So now here you can see in these figures that if I have these three decision boundaries with the name L1, L2, and L3, so in logistic regression I was taking arbitrary decision to select a line or decision boundary, but here what we are doing is we are selecting a decision boundary we are selecting an optimal decision boundary based on the concept of maximum margin. So I tried to explain all these things with the help of different scenarios. So in scenario number 1, we took a very simple example in which we had 2 classes and we have 3 decision boundaries, but only one decision boundary, which is B here, is able to successfully classify these 2 data points. So we were in a very easier state that we could select the decision boundary B as our classifier. In scenario number 2, we move to a little bit of different situation in which we again have 3 decision boundaries, but all these decision boundaries are able to successfully classify the data points. Now the target is to have a one decision boundary which is an optimal decision boundary. And how can we achieve an optimal decision boundary in SVM? We can have this by calculating the distance of a data point to the decision boundary, and this distance is basically known as a margin in support vector machine. So the target is to calculate the distance of each data point to each decision boundary, and we can select a decision boundary which have this maximum margin from each data point. So on the basis of that, we can say that we have selected an optimal decision boundary. Now in scenario number 3, what we saw is that it can happen that we can have an outlier, or we can have some kind of noise present in the data set, due to which maybe some samples of this data set may lie on the other class of the data set. So in that case, if we have 2 decision boundaries here, we can see that we need to go for a decision boundary which could basically classify the data points correctly, right? Even in that case, the support vector machine will not be looking for the maximum margin here. So in scenario number 4, we had a more complex situation in which we had a data point here which is very close to the class which is the second class, or the class which does not belong to this data point. So we can say that in this case, the outlier or the noisy bit is very close to the other class of for the classification. So in this case, the only option is to bear this data point, because we don't have any situation through which we could separate this data point. So in such kind of situations, we need to bear some kind of misclassifications. So we will see that how many data points we are classifying correctly and how many data points are being misclassified. So if the number of misclassification is very less, like in this case there is only one misclassification, then we can bear this loss and we can say, okay, since most of the data points are being classified correctly, so I can bear this loss of one misclassification. Of course, this misclassification will have an impact of the overall accuracy of the system, but since there is only 1 or 2 data points which are being misclassified, so it will not have a major impact on the accuracy of the system, and we are in a state to bear this loss in order to perform the classification of these kind of situations. Okay, after discussing all these scenarios, we further discussed some definitions related to different terms which are being used in support vector machines, and we saw initially that what are support vector points in a support vector machine. So we saw that support vector points are the points which are very close to our decision boundaries, right? And these support vector points are basically playing an important role in the placement of the decision boundary. So if I remove a support vector point, or if I add a support vector point, it will have an impact on my decision boundary, and it can move my decision boundary. However, on the other hand, the rest of the data points, like these data points here and these data points here, these data points are not being considered as my support vector points, and even if I remove these points, they will not have a major impact on the position or on the decision boundary itself.